Welcome back everyone. In the previous video, we have discussed about computer systems, its four major tasks, and its hardware and software components. We have also emphasized at the end of the previous video that designing the hardware and developing the software are done separately by two groups of people. What links the hardware and the software together is the computer architecture. By knowing the computer's architecture, software developers can create softwares without knowing how the hardware was built. So what is a computer architecture? Computer architecture refers to the computer's attributes that are visible to a programmer. This includes the assembly instructions, data bit words, I/O mechanisms, addressing modes, and many more. We will talk about this further next week when we talk about the MIPS architecture. Computer architecture answers the questions, is there a multiply function, or what other functions are available to create a program? Meanwhile, computer organization refers to the organization of circuits and other hardware to implement the features in the architecture. This includes circuit modules, control signals, interfaces to and from peripherals, memory technology, and many more. It answers the question, how will the multiply operation be supported in hardware? If you still can't understand our definitions, this table is a summary of the differences between the computer's architecture and the computer's organization. Computer architecture describes what the computer does, while organization describes how the computer does it. In design order, a computer's architecture is designed first, while organization is designed after finalizing the architecture. A computer's architecture realizes its hardware, while a computer's organization realizes its performance, like speed and power consumption. Computer architecture includes logical functions such as instruction sets, registers, data types, and addressing modes, while computer organization consists of physical units like circuit designs, peripherals, and others. Computer architecture is also called instruction set architecture, while computer organization is frequently called as microarchitecture. Based on this table, we get that computer organization is based on its architecture. So let's talk about some notable architectures that are used today. One of them is the ARM, or the Advanced RISC Machine, which is common in mobile devices. Another is the x86 architecture, which is common in Intel processors. The MIPS architecture, which is typically found in embedded devices. This is the architecture that we are going to discuss in the course. And there's the open source RISC-V ISA, designed to support a variety of applications. There are more architectures out there, and most of them can be classified in terms of instruction operands, memory structure, or complexity. However, due to the popularity of parallel computing and multiprocessors, another classification has emerged recently called the Flint's classification. Computer architectures can be classified by how the memory is accessed through the instruction set. Memory-to-memory architectures like the VAX and PDP series uses up to 3 operands per instruction, where 1 or more operands can access the memory. Register memory architectures like the x86 and Motorola 68K uses up to 2 operands per instruction, where only 1 operand can access the memory. The MIPS, Sun, Spark, and ARM follows the load-store architecture. In this architecture, only the load and store instructions can access the memory and transfer the data to the register file. Then there's the accumulator-based architecture, which uses only 1 operand per instruction. It uses a special register called the accumulator, hence the name, when an instruction needs 2 operands. A supplementary video discussing these architectures with samples and comparisons is provided in the study guide. Make sure to watch this 10-minute video so you can understand more about it. Now let's look at how computer architectures are classified by memory structure. There are two popular architectures under this classification. The first one is the von Neumann architecture, also called the Princeton architecture. This is the simplest architecture and is somewhat what we have been discussing so far. So in the von Neumann architecture, both data and instruction are stored in a common memory, and the common bus is used to transfer both data and instructions throughout the system. Because there's only one bus to use, data are transferred one at a time. Instructions are also read one at a time and in order. You can check out more details about von Neumann architecture in Google during your free time. What is good about this architecture? Well, since the architecture is simple, it is also simple to organize. What's bad about it? The single bus architecture makes it slow. Even if you make the processor and memories faster, data and instruction transfers still depends on that single bus, which is its bottleneck, the von Neumann bottleneck as they call it. This bottleneck was addressed by the second architecture called Harvard architecture. In this architecture, there is a separate physical memory for the data and instruction. Aside from that, there are also two separate buses that enables the access of data and instruction at the same time. So what's good about it? It generally has faster processing because it eliminates the von Neumann bottleneck. But there's a trade-off. The two separate buses will definitely add more space and pins on the processor. The control unit will also be more complex since data and instructions are accessed at the same time. There is also the issue that the memory is not maximized properly because the free space in the data memory cannot be used for instructions and vice versa. So the memory dedicated for each unit has to be balanced carefully. Most computers today adopt a combination of von Neumann and hardware architecture. Collectively, they are called modified Harvard architecture. It loosens the strict separation between the data and the code while still maintaining the high-performance concurrent data and instruction access of the original Harvard architecture. There are three main modifications of modified Harvard architecture. In the split cache architecture, there's a data cache and instruction cache, which looks similar to Harvard architecture. But the main memory still contains both the data and instruction, similar to von Neumann architecture. In the second modification called instruction memory as data architecture, data, particularly constants, can be stored in the instruction memory. The data in the instruction memory is accessed using a special set of instructions, while the data memory just contains data. The third modification, the data memory as instruction architecture, is like the reverse of the second, where instructions can be stored in the data memory. Another classification of architectures is based on its complexity. The two popular architectures here are the CISC and RISC architectures. The Complex Instruction Set Computers, or CISC, is a computer architecture that aims to make program size smaller using complex instruction set. The idea is to increase the overall speed of execution by requiring less memory cycles to execute the programs. Some processors that use CISC architecture are Motorola 68K, DEC VAX, PDP-11, and Intel's x86 and 8051. On the other hand, the Reduced Instruction Set computers, or RISC, use simpler instructions to make the hardware design simpler. So MIPS, PowerPC, Atmel AVR, Microchip PIC, ARM, and RISC-V all use RISC architectures. To know more about CISC and RISC, let's do a comparison. CISC has a large number of instructions, usually hundreds of instructions, while RISC only has few instructions, typically about 100 or less. CISC program sizes are smaller, thus they require smaller RAMs, while RISC program sizes are larger and requires bigger RAMs. This is because it takes multiple RISC instructions to do a single CISC instruction. CISC has variable length instructions and are usually more than one word size, while RISC instructions all fit in one word. And since CISC uses complex instructions, its instruction decoding is also complex, while RISC has simple instruction decoding. CISC are usually used by memory-to-memory or register-to-memory architectures, while RISC is usually used by load-store architectures. And because of that, most of the CISC instructions require multiple clock cycles to complete, while most RISC instructions can be completed in one clock cycle. And lastly, in CISC, additional transistors are used for storing complex instructions, while in RISC, additional transistors are used for additional register file. The equation above is called the performance equation or CPU time, which computes the amount of time a program is executed. CISC and RISC architecture both aims to reduce this performance parameter. CISC targets to decrease the CPU time by decreasing the instructions per program while sacrificing the cycles per instruction. RISC, however, does the opposite by reducing the cycles per instruction while sacrificing instructions per program. You may wonder which one is better. Well, I think CISC is better for programmers while RISC is better for computer engineers. Anyway, many computers still remain in CISC, but as the complexity of high-level languages increases and as the cost of RAM decreases, many computers switch to RISC architecture. Because of the popularity of parallel computing and multiprocessor computers, another computer classification has emerged based on the number of instruction and data streams that can be processed simultaneously. This is called Flint's classification, and it's classified into 4 major categories. The first category is the single instruction, single data stream. This can be seen in uniprocessors that typically use von Neumann architectures where instructions are executed sequentially on a single dataset. The second category is the single instruction, multiple data stream. In this category, all the processors execute the same set of instructions on different data streams. This architecture is used in scientific computing that involves parallel processing, like array computing and vector processing. The next category is the multiple instruction, single data stream. In this category, all processors execute multiple instructions on the same dataset. A few machines are built using this architecture, but they are not commercially available because they are only used for theoretical purposes. The last category is the multiple instruction, multiple data stream, where the processors execute different set of instructions on different data sets at the same time. This category is seen on multiple processors that we have these days. In our course, we are going to use the MIPS architecture. It is a load-store RISC architecture developed at Stanford University in the early 80s. The readings and idea sessions with graduate students during the development of this architecture launched the development of one of the first RISC processor. It has 111 total instructions, each represented in 32 bits, and each is processed in one clock cycle. MIPS processors use a technique called pipelining to more efficiently process instructions. We will talk more about MIPS architecture next week and the next succeeding weeks. I hope you enjoyed this video and you were able to understand how organization is different from a computer's architecture. I also hope you understand the different classifications of computer architecture. On the next video, we are going to talk about embedded systems and the role of microcontrollers in designing embedded systems.